Happy morning, and I welcome you all once again for the AICT sponsored FDP on electric vehicles. I have a pleasant duty of introducing today's resource person, Dr. K. Palanisamy, Professor, VIT Vellore. He received his bachelor's degree from KSR College of Technology, master's degree from Coimbatore Institute of Technology, and Doctor of Philosophy from Vellore Institute of Technology. He is currently Associate Professor of Energy in Power Electronics Division and in charge of Center for Smart Grid Technology at VIT. He has received DSC grant of 1.2 crore to establish PHIL-based microgrid testbed. He has authored over 96 scientific papers in journals and conferences. He is a certified energy auditor by the Bureau of Energy Efficiency, Government of India. He has taken up various consultancy projects in energy efficiency and power quality improvement. With an immense pleasure, we call upon our resource person, Dr. K. Palanisamy sir, to share his knowledge on challenges and opportunities on electric vehicle charging infrastructure and its impacts. Sir, over to you, sir.
Morning all. Good morning, madam. Thank you very much for the nice introduction. I'm very happy to be a part of this ACDP. Today, the topic of discussion is right, the smart charging station, or we can say the infrastructure required for handling the fast charging, right, or rapid charging. Okay. See, I've just shown, of course, these are all very, old, and most of you must be knowing that the different levels of charges and, its application, range of, and time required to charge the vehicle to the full, size. So that is given actually. In fact, the today discussion, is all about how are we going to meet or handle this kind of requirements, right? So that's what the thing actually, especially the level 3, that is fast charging. When you say fast charging, it may not be directly applicable to you, like when you have one car and you are going to charge in your home, right, or in your apartment, then it will not be applicable directly to you. But in case if at all, like a commercial charging station is established with at least 10-15 charging points, then we are talking about them. Our talk is about them, right? So with this, just we will get into this one. Whenever the new challenges, or you can say the new issues are coming, right? So that also brings a lot of opportunities. So every challenges can be converted into opportunities. So that in that aspect, because of the large penetration, it is expected, and it is already there in some of the developed countries, and it is going to come in developing, almost developing countries in near future, right? So when you say the challenges, right, are different issues related with the fast or rapid charging, and these challenges gives a lot of new business to the people. So the new business sectors can be split into the electric power market, or you can say the electric power network, and associated people will get a lot of business, right? And of course they are, yeah, they are going to solve the challenges, so they will get normally a good business, right? Then there will be an issue, and of course when you say issue, that how are we going to solve, and based on that there will be some business. So renewable energy integration, then transportation system. So when I say transportation system, I'm not going to talk much about the growth, or the features of EVs, and other aspects. I'm just talking about how the transportation system is connected with the power system network, right? So that allied business, right? And charging infrastructure, yes, that's the point of focus. When I say charging infrastructure, I'm just converting, or I'm just taking the advantage of smart charging station, right? So what exactly is smart charging station, how it addresses all the issues, and how it helps to the power system network. So that's the focus today. And distribution system planning, of course, when I say smart charging station, that will very well taken care. by yes. Okay, right. See, when we talk about electric power network, see, EVs are equipped or coming with a battery storage. That too, when I say above the medium level, like a very good sophisticated electric vehicle, then it must be having at least 50 kilowatt plus, right? 50 kilowatt hour plus. Let's say, right? So when we say energy storage, we have a flexibility attached with the battery storage or energy storage, right? Uh, See, when we say charging, right? And when we convert the charging into smart charging, coordinated charging, right? Then we can take part in the electricity market, right? And once if you say I can take part in electricity market, I can actively participate in electricity market, then you can also do some kind of ancillary services, right? So when you say ancillary services, yes, when there is a mismatch of generation and demand, being a smart charging station, controller or holder, right? What I can do, I can, aggregate the entire vehicle stopped and parked at currently at charging, can take part in frequency regulation service. It means like I can, balance the mismatch between generation and demand, right? That I can do via vehicle to grid. And of course, right? See, if at all I'm doing that, so I have a, provisions to aggregate the entire vehicles parked at my station or at my charging station, and I have the data. It means I have a privilege to access the data of all the SOC and kind of other details, and also the driver's preference. Like, so if I say smart charging station, you're not just connecting to the charging point to get charged. You're also going to give some kind of input, right? Or it can be what is it derived from your past preferences, right? How long I'm going to stay, and what is the purpose I'm staying here? It's only for charging or something else. So based on these preferences, the smart charging station will take some kind of decisions. It means, yes, this particular user or this particular EV owner is allowing us to access the the EV charged energy, that is EV battery energy, right? So it means if I have the data along with the associate of that particular EV's battery, then I can take part in the frequency regulation. It means by supplying the active power by aggregating the entire EV spark there to do some kind of ancillary services to the grid, right? So of course that is V2G, vehicle to grid, right? Okay. So electricity power market is getting some advantage when I have all these kind of smart data. It means the vehicles are parked not only to just to charge. I have, or the EV owners are having provision to enable, like, yes, if the cost is less, maybe you can allow me to charge. If the cost is more, if I have energy in my vehicle, please take it and pay something or comment something. So in that way, if I have a data, I can use all those data, consolidate all those data, and from that I can do the grid ancillary services, support services, right? Okay. See, grid support services, or you can say grid ancillary services, are at present paid heavily, right? It means if I declare or if I show some kind of firm energy backup by aggregating the entire EVs who are attached with me, right? See, it is something like I can declare, yes, at any point of time, I have, like 1 megawatt hour of energy with me, right? So, it is something like by having the knowledge of all the parked vehicles, I can say, yes, this is the amount of energy I can firmly say or I can firmly support to the grid. So 1 megawatt of hour, right? So, these grid ancillary services are for very short time. It varies from seconds to minute. It's not for hour or it's not for, days together. It's for just seconds to minute. So see, again, of course, we are supposed to understand what are the, services coming under grid ancillary services. It can be frequency, regulation services. It is something like when the frequency of grid is going low, during that time, by having this film energy, I can support or I can supply some kind of active power so that the frequency can be regulated, right? So that is one kind. Or I can do the voltage support, right? If at all grid is facing the low voltage issues, I can support. I have some infrastructure. Of course, I'm not talking about active energy at all. With my infrastructure, that is smart charging station infrastructure, I can support to the grid to get recover from the or get restored from the voltage issues, right? So all those things I can do if I have a smart charging station, right? Then see, most of the smart charging stations, when we say, it's all associated with the green power, right? So your charging station, maybe if you have a parking slot, above the parking slot, definitely you'll have 3 kilowatts of solar panel. And if it is in highway, right, the remote area, then you can have, you have a privilege to use the windmills. Of course, it's based on the location, the wind data and other things. So you can have that, and of course you are going to have a hybrid energy storage system. So with all these things, right, I have a renewable energy sources, I have hybrid energy storage system, and I have the smart charging station facility. So if this is the case, the biggest drawback of renewable energy is actually the highly intermittent, right? It's varying highly. Okay, those variations can be suitably compensated with this kind of smart charging station. You need not think about it as vehicle to grid. All the time we are not going to access the energy from the vehicle, because when we say that, then the number of charging and discharging cycle will increase. So that will affect the lifetime of the battery. So it's not just VTG alone. It's connected with the your hybrid energy storage system and everything, right? So if I have smart charging station with a reasonable size of hybrid energy storage system, I can compensate suitably the intermittent nature of renewable energy sources. So that will not be a problem to me, even if it varies, to the wider, gap. So that is possible. So renewable energy integration can be converted into a film power source. That is one advantage if I have the, a large penetration of EVs and its charging infrastructure. Then the transportation. So as I told you, see the transportation system, I'm not going to talk about, the EV mechanics or other things actually, or the, what is that, other, support. I'm just talking, or I'm just connecting the transportation system with the electrical network, right? So by coordinated charging, right, you must be understanding, or you must be knowing that in many of the developed countries, they have established V2X, right? It can be vehicle to vehicle, it can be vehicle to charging station, it can be vehicle to transportation, a smart traffic system, it can be anything, right? Smart city management, or it can be smart city, the data, so it can be anything. So V2X communication enables not only, see, I'm talking about the communication. The V2X communication enables the charging stations to plan, yes, uh, for the next 1 hour, how many vehicles I'm going to get approximately. So how much energy I have to, prepare to charge it, right? Or if at all I know, like those vehicles will come and stay for this many, minutes or hours, then also I can plan, the grid answer services, or if someone asks, rapid charging and he need to pay heavily, that's a different thing actually. So I can support with another vehicle. So that also I can plan based on the data. So that's what transportation system connected with the power network or charging network, right? Then distribution system planning, yes, this also I can do very well. So definitely inappropriate plan. It means if I'm not using the coordinated charging, then definitely I will end up with the voltage instability issues, frequency issues. Because see, if at all we are talking about fast or rapid charging, even if I assume very less number of vehicles at a time, if it needs charging, then it leads to sudden rise of demand. So your distribution system or your power system cannot support the sudden ramp, the sudden rise in demand. So that need to be addressed properly. If I have again the large scale energy storage system, the V2G and other mechanism. So that's what the charging infrastructure and distribution system planning. Okay. So at the outset, if you say the need of smart charging system or the capabilities of smart charging system, it is almost like a grid operator, right, or transmission system operator or distribution system operator, right? We also, the EV charging infrastructures or the networks of EV charging stations also need an aggregator, right, for coordinated charging and discharging. With, of course, as I told you, we are going to talk green, energy based charging station. So coordinated charging and discharging, forecasting of all renewables, and energy storage system. With the optimal size of energy storage system, how I am going to handle. So I need an aggregator. So that's what actually all about the smart charging station. So when you say smart charging station, there is an aggregator, right? That aggregator will have a bidirectional communication with vehicles, not only with vehicles, with all other smart city infrastructure or associated data. So he must be having access to get traffic, the nearby or the vehicles which are entering to the cities, right? So all those, right, details are connected with the aggregator, and he will plan accordingly, right? So based on all these, our discussion is mainly targeting the recreation, because as I told you very clearly, it is not for one EV and he is going to charge in his home. We are not talking about that. We are talking about the group charging, or you can say the commercial charging points. So the target is recreation clubs, shopping malls, theaters, sports complexes, and the commercial charging station. So all these places will have a combination of fast or rapid charging, normal charging, or he it means the vehicle owner can give an option. Yes, you can access my energy which is stored in the electric vehicle battery, right? So he can give the access. So if he is enabling that feature, then he can earn something, right? So all these things need to be planned properly. So that's what all about this. Okay. So finally, you have EVs, you have renewable sources like the solar and wind, and these are all highly intermittent. And the other side is EVs also. The frequency of arrival or the charging pattern. It means the expectations of the EV owners. He may prefer to charge normal. He may prefer to charge rapid, right? He may need to charge his vehicle within 5 to 10 minutes. That is also possible with the present technology, right? So all these will lead to the requirement or the importance of EV aggregator or load serving entity, right? So if you have all these things in a smart way, then you can participate in energy market, right? You can help the grid ancillary support services, right? So they have energy market. So it means you are forecasting the EV's arrival and their charging pattern or charging preferences, and you are forecasting the wind, you are forecasting the solar, and you are also forecasting the load in the commercial the campus, or you can say smart community, right? It can be a shopping complex, it can be a theater, or it can be a mall, it can be anything. So you are forecasting everything. See, this involves demand side management, then aggregated charging and discharging, and also you are participating in the grid support services. So all these things. So energy market, when you say, like, you are involving in all these levels, right? And ancillary services market, as I told you, you can support in frequency regulation. You will be paid heavily, right? But for that, you have to show a firm energy storage of a particular or a considerable size, right? So you can participate in the regulation service market or reserve service market. This is something like that's what I was telling. By having the knowledge of EV's arrival or their charging pattern and SOC of my hybrid energy storage system, or if I have a forecasted data of my renewables, and also if I know the status of my distribution system, then I can show, yes, at a particular instant, if at all the grid requires this much of active power as a lump sum, right? Or as I told you, all these ancillary services very short time. So I can show this much of megawatt hour I can give or I can take. See, this is not only just supplying. This can be like when the frequency is high, you're also supposed to be or you're supposed to take the energy, right? That can be used to charge your hybrid energy system, or like the road load regulation, all those things you can plan it or you can use it. So that's reserve service market. So you are showing the hybrid energy storage system along with your vehicles, parked vehicles, and you're showing us, yes, this much megawatt, right, or megawatt hour I have, and capacity service, that is also right, you are participating, right? So in near future, the EVs are what is the growth in numbers, right, are going to be huge, definitely, right? That is one thing. And so this, the EV charging load is relatively small now. Of course, this, when it is small, it is better to plan how or what are the protocols I need to follow, or what is the algorithm, I can say, right? Like control management or power and energy management, everything, right? So you can manage by considering the vehicle to grid, right? Uh, see, there are good amount of research going on, like if you allow vehicle to grid, what will be the benefit in terms of charging cost, and what are the drawbacks, like you are losing the battery life, because even when you change the direction of current to the EV's battery, it will be considered as a cycle, right? So the, to some extent, right? So when when you involve this V2G, it is ultimately end up with more number of charging and discharging, or more number of cycles. So you are losing the life of the battery, right? So there must be a balance between the benefit and the the losing of, or the life, or accelerated aging of the battery, and all these things, right? So that's need to be worked out, right? There must be a proper financial policy, or you can say what is it, the regulation, right? So to what extent we can allow V2G, right? If if you allow V2G, what is the ratio of getting benefit, financial benefit, and at the same time, what is the possibilities of, what are the possibilities of losing my the EV battery life and other things, right? So that must be planned. So this that's need to be worked out in a what is it, extensive way. And see, the biggest advantage I can say with EVs are the charging pattern is not rigid, because it's electrical system. The time constant is very rapid. So if that is the case, so I can convert the EV charging into a very flexible, right, entity, or flexible the load, right? So that's the advantage I will get if I coordinate and do the smart charging. So again, based on that, these are the things like grid load, energy storage system, EVs, and renewable sources. So how I'm going to help to film this one, convert into a constant power smoothing, right? And distributed thermal generation, how optimally I can use this one, right? So that I can take part in this, right, electricity market and everything, right? Okay. See, I'm just keep on saying that the hybrid energy storage system. So when I say hybrid energy storage system, this is something like my energy storage system should have high power density. At the same time, I should have a reasonably good or strong energy density, so that I can give backup for long. Also, I can support for rapid charging. Even if I have, let us say, 15 charging points, if all the 15 charging points are expecting the rapid charging, yes, I should be in a position to support those things, right? So when I say high power density, yes, my hybrid energy storage system should involve the super capacitors, or flywheel kind of energy storage system, or super magnetic energy storage system. But of course, the flywheel or super magnetic storage systems, all those things are are very costlier things at present, because only it is at demonstrated level, right? There are not much, or there are not many what is it, working models or working projects in terms of flywheel or super magnetic storage system. Those are very few, right? That too, if you take very high energy density level, for example, few 100 megawatt hour, right? Those projects are very less, both flywheel as well as super magnetic storage systems. Those are very fast. You can just support for a high ramp. It means if the charging station is facing a huge number of rapid charging requirement, immediately this kind of things like super magnetic storage systems or the flywheel or this capacitor will support, right? Okay, this is one thing. And there are a lot of research and good number of outcomes are derived from the literatures, and that is proving that the used, it means the EV batteries will lose its life. It means the range, the miles. If it reaches around 50%, then they can replace. It means they can sell it and will go for new batteries. Those used 50% range batteries can be utilized for the large scale energy storage system, which will support for smart charging station, or you can say grid level energy storage system, right? That is one thing, right? So that's what discussed here. So at the if you cover up everything, the smart charging station should be capable of taking care of green energy production and its intermittency, and taking care of state of charge and state of health. You have to manage optimally the energy storage system, and you should not at any instant in a smart grid environment, the entire charging infrastructure should be a flexible load. At any time, based on the request or based on the command, I should reduce my power consumption or I should increase my power consumption. It means I should take part in the the grid support services, right? So I must be a very flexible load. So only then the grid operator will operate smoothly or will perform his duty, right? And of course, the smart charging station should be positioned to access all these vehicle data, right? So and the forecasting of vehicles which will be expected in the near future, right? From the nearby areas, right? Okay. So ultimately we should reach the sustainable energy system, that too with the renewable energy sources, especially solar and wind. And definitely EV charging must be smart, right? By using vehicle to grid, then the entire thing, as I told you, the entire charging station should behave like a flexible load, right? Then the size of the hybrid energy storage system also optimal, right? And as I told you, like we are going to use the used batteries from the EVs as a grid level energy storage system. So you will get some cost benefit, right? So all those things should be taken care in the smart charging station, right? So finally, this is the project currently we are involving with Aalborg University, Denmark, and University of Bologna, Italy, and SC Nordic is a industrial partner from Denmark, right? And of course, from our side also, we have some collaborators. So we are, of course, it's in a proposed level. It's not at sanction, from the EU, European Union, Iran proposal, right? See, part of the things are realized already there as a parts and keys in our VAT. I'm going to show you that video also. See, we at VAT, we have the provisions of smart charging station. This is actually, it's not exactly to the what is the grid level or very high power rated. We have up to 15 kilowatt hour as a real hardware and associated converters. The remains we are going to realize from the power hardware in loop. So in VAT, we have a PHIL environment, power hardware in loop environment. This is realized with the help of OPAL RT 5700. It's a real-time RTDS, real-time digital system simulator. This is something like, in the simulation, it's fully, your control is simulated model, and your source or load, everything is modeled, right? And if you go little, above, maybe you can realize your hardware in your FPGA or DSP or kind of hardware environment. That is controller in a hardware environment, and other systems like your power systems or your source or load, that is in the model, it means software. So that is controller hardware in loop. we we went to the next level, that is power hardware loop. This is something like the grid can be realized, grid can be modeled in the system. It can be MATLAB, or it can be any other simulation environment. And a part of load, it means the regular EV charging, right? And some sources like PV, maybe 10 kilowatt, 10 kilowatt, wind can be 10 kilowatt, and we have also programmable load that can realize a smart home, right? So that is also we have in our VIT. So all those things connected to the grid via power amplifier. Power amplifier is something like, you can say very simply, it's a grid emulator, right? It's a hardware. You can exchange the power, real power with them. Real means like really power with them. Like so, it's a bidirectional. It means you can operate in 4 quadrant. So bidirectional converter, right? So it is connected to the grid via a controlled environment. That is a back-to-back converter, power converter. So that will be operated or controlled with the help of, or with the polarity, that is 5700. So we have this one, and solar PV system. See, we have planned for 500 megawatt, and part of the system is a real hardware, can be 50 kilowatt. And similarly, we have hybrid. We have a super capacitor. We have a lithium ion, lithium phosphate battery. So that is also we have a part, and the remaining is realized in the software. And we have wind generator, it means wind emulator we have, and all these things, right? And we have also smart load, right? So what we are trying is, we are assuming the entire thing except grid, we are assuming this as a smart community. Smart community can be your university or your college campus, where you have a parking slot, you have a different load, you have you can have a PV, you can have a wind, you can have all these things as a part, right? And you are connecting, and you are suitably managing, or by having a proper controlling hybrid and solar system, you are managing the smart charging station. It means at any instant I should not go beyond the allowed power ramp. It means I cannot increase my demand beyond certain slope, and similarly I cannot go below certain slope. It means I'm always maintaining the grid power drawal as a constant, right? By ensuring that with the help of this hybrid energy system. So that's what we are trying, and we are trying to show how the hybrid energy storage system, along with the electric vehicles, I can do some kind of frequency regulation, that is grid support services, right? That's what our project proposal, and we are trying that. Okay, so we have realized PHL based microgrid and control, and we have smart charging station. It's around 15 kilowatt hour, and we have also planned, or we are working on demand side management. See, you must have heard about electrical spring, right? That's like a virtual energy storage. This is something like, see, I have a load. By adjusting the voltage, so let me assume like the load is kind of resistive. So when I adjust the voltage, the V squared R can be adjusted. So it's a converter. It's a converter. By suitably adjusting the voltage, I can vary the power consumption of this load. Let's say the fan, right? If I adjust the voltage, if I reduce the voltage, the consumption of the fan, right? Power consumption of the fan will come down. So in this way, I can involve in demand, side management as well as response, right? So I can do both. Okay, right. So now I just want to show you that, a video, what we have realized with our institute. Just look.
The Smart Grid Laboratory at VIT Select has evolved from the liberal funding thanks to the award grant by Department of Science and Technology, DST FIST, along with equal funding from VIT Vellore. The laboratory houses a 100 kVA smart microgrid test bed based power hardware in loop PHIL setup. The setup comprises a 100 kVA grid simulator, wind and solar emulators each of 10 kVA, 5 kilowatt hour hybrid energy storage system with lithium ion battery, super capacitor rated at 160 farad, 1 kilowatt proton exchange member fuel cell, along with a 5 kilowatt programmable load. The components of the grid are controlled by Opal RT 5700 controller and LabVIEW. Different case studies related to power and energy management, fault ride-through, low voltage, high voltage ride-through, and virtual inertia emulation can be tested. Some of the unique features of the setup include realization of hardware in loop, controller hardware in loop, and power hardware in loop. The focus of the research laboratory is on microgrid power management and power quality improvement.
So this is the infrastructure we have developed from the DST FIST fund. I hope you must be knowing that it's a 50% contribution. See, we established like 100 kVA grid emulator. It means microgrid system, which I can show you that. Yes, these are the setup we have. We have a grid emulator of 100 kVA, and this is the program load, and this is the fuel cell of 1 kilowatt, and we have integrated everything through this test bed, and we have OPOLARITY 5700. This is what I was telling. It is a power hardware and loop controller, and just behind this table we have a that is this one. Have a wind emulator of 10 kilowatt. This is a PMSG based wind emulator. I can just plan the wind profile and give it to the controlling the shunt motor. From that I can get the wind emulator operation. And this is 1 kilowatt fuel cell I was talking about. And we have a battery of lithium phosphate, and we have a solar PV emulator, and we have a super capacitor, and of course OPOLARITY we have 4200 also. This OPOLARITY, this is something like we have distributed the control system. This main OPOLARITY 5700 will take care of the measurement and power quality improvement at the integration point of common coupling of PV emulator, wind emulator, the hybrid energy storage system, fuel cell. So in that point, it will measure all those things. Accordingly, the energy management can be done through this grid emulator. And this OPOLARITY 4200 will take care of the control of wind emulator as well as the PV emulator, feeding the solar profile. And also the SOC, SOH of these hybrid energy storage system can be taken care by another OPOLARITY 4200. So this is how we have we have realized the smart grid system. At present we have done some kind of power management, the microgrid control we have done, and we have ensured the power quality at all the levels, and this through the grid we are injecting the scheduled power, and also we are drawing the scheduled power from the grid emulator. So this is what we have realized with the help of Albar and University of Bologna, Italy. So our intention is like to study what will be the impact to the distribution system if I have uncoordinated rapid or fast charging, right? So you can understand the charging point can be only at DC level or it can be AC level. So here we can see like there is energy storage, PV, and if you want some other new energy sources, you can connect it, and also you are connected to grid, right? What you are supposed to ensure is in a smart grid environment, you are not supposed to increase or decrease the power drawal, just like that. It means there must be a allowed power RAM. You cannot go beyond a particular power RAM. It means for a minute you cannot go beyond 5 kilowatt, right? So from the last minute to this minute you can just increase or decrease only 5 kilowatt, right? I'm just telling the example. So there's a fixed power ramp up or power ramp down that you are supposed to maintain with the help of hybrid energy storage system, also with the MPPT control and other things, right? So if you have what is it, the reasonable size of a reasonable level of SOC and the PV backup, you can do with this alone, or you can control the charging pattern, right, of these vehicles. So that is one thing. The same thing can be done with the the AC also, or AC level also. So this can be one uh, well established charging infrastructure. Uh, yes, there must be a power factor, input power factor corrected AC to DC, that active front end rectifier. This is called active front end rectifier with the help of the controller, and DC DC also you should do. Then there's a isolation that's required. So we are doing DC to AC at very high frequency, then it is transferred, then rectified, and it is feed into the electric vehicle, right? And most of you must be knowing that almost most of the EV charging are like constant current and constant voltage. So initially constant current, so that the rate of charging will be higher or faster. Then once it reaches a certain level, then the current will start to decrease. So you are going to constant voltage. So constant current and constant voltage charging only you are doing, and this is how the the charging pattern will be. So initially, since it's constant current charging, you can see the power drawn from the charging infrastructure is somewhat increasing initially, right, for 2-3 minutes. Then once the voltage is established, or you can say once it is coming out of constant current charging mode, then the power drawn from the charging infrastructure is coming down, right? And your SOC pattern will be like this, right? And you can understand, see, for 400 volt, the battery, when it is fully discharged, it will be somewhere around 355. And it is fully charged, when it is fully charged, it will reach around 405, 406 at that range, right? So the SOC is varying from 12 to 94%. You can see, this is somewhere around 12%, and final charging state is actually 94%, with the peak value of 117.2, right, kilowatt, at 16%. This is reaching at 16% of SOC. Okay, right. This is exactly after 2 minutes of charging starting point, right? So constant current mode lasted for only 2 minutes here. After it is constant voltage mode, right? So all these things should be supported by your smart charging station. So this, one from one paper. See, as per this, if you see, the incoming feeder is having 1300 ampere protection, and you have a good amount of storage, right? 400 kilowatt hour of battery. Okay, right. See, to enhance the life of the grid level, or large scale energy storage system, what we can do, you can just group the energy storage system into two, right? Maybe if I have 500 kilowatt hour, I can split 2 into 250 kilowatt hour. Why? That is, that's the key actually, or that is the point we have to understand. See, if you convert, or if you divide the total capacity into two, if one size of the battery, or one group of batteries involved in charging, right, the other group of batteries will be discharging to charge the EVs. So I have a large scale energy storage system. I'm dividing into two groups, that is 250 kilowatt, 250 kilowatt each, and one 250 kilowatt hour is giving the energy. During the time, the other 250 kilowatt hour is getting charged, right? Of course, if you have simultaneous, if you have more number of EVs expecting fast charging or rapid charging, of course you can club both the group into discharging mode, so you can discharge, and during the time this will the EVs will be charged, right? But you have to optimally manage the SOC, right? The state of charge of batteries need to be optimally maintained. It means it should not be fully charged, so that let's say for one particular instance, I have good amount of PV energy, and my grid frequency is also good, beyond the rated, like instead of 50, it is 50 point something. So during the time, you are expected to draw the power. So that time you should not say my entire energy storage system is fully charged, right? And there's no vehicle, unfortunately, okay, to charge. So during that time, you should have a cushion to charge. It means to take energy from PV as well as draw the power from grid, because it is cheaper. Similarly, when more number of vehicles arrived together at same time, you should not say I know I'm fully discharged. So you cannot draw or you cannot increase the power required or power from the grid, because you are not allowed to increase or go beyond certain power RAM. So you should be within the limit, and the remaining power should be taken care by the hybrid energy storage system or the groups of battery, right? So all those things are worked out. Okay. And this is actually, as I told you, this is big battery or large scale energy storage system, and supported with supercapacitor to take care of fast charging. And I have PVs, as well as I can have some winds, and I can charge all the modes, like level 1, level 2, level 3, all the modes I can charge it, right, without disturbing much, right? This is my grid. So at any instant, I should not go beyond certain level of power. Similarly, I cannot reduce my power drawn. So both should be ensured, so that I can say, yes, as far as the grid is concerned, I'm a constant power load, right? So that I must ensure. Similarly, when the grid requests some kind of support, I should do, right, with the help of this and this. And V2G is enabled, then I can support from this also. So that's what actually the smart charging station should do. Okay. See, the smart charging station need to face or need to address many issues. One important issue, I'm going to show you now. This is the measurement we did in our campus, that's VAT campus. So we used to do the long time energy monitoring, or the electricity parameters monitoring with a fluke meter. So this is one particular week data. You can understand during the daytime, it means 6 a.m. to 6 p.m. You can see this is the harmonic level, right? Uh, you can see I have selected harmonics. During daytime, right? During daytime, most of the days see my harmonic level. It is just like that, beyond 30%, 40%, 70%, right? Even sometimes it is reaching 100%, right? And above, right? What it means simply, see, then you have, good amount of rooftop solar PV. Of course, in VAT, we have 2 megawatt of rooftop solar PV, and our current load is 9 megawatt. And you must be knowing that we don't have any students in our campus right now, right? Except some, foreign students, like African and other students. We don't have any students now. And of course, our faculties are coming. So the load is very less, but we have 2 megawatt of rooftop solar PV. So the unfortunate thing is, or you can say the bitter part of the solar PV generation is, the solar PV plant will supply only a pure sinusoidal current with a unity power factor, right? But in the other side, most of our loads are LED lamps, and most of our lift or UPS, many things are non-linear loads. It requires the harmonics, it requires the distorted current. But my solar PV will supply only pure sinusoidal current with the in-phase quantity, right? So it means it will not supply any kind of reactive power. So the entire active power, even more than that, I'm getting from the solar PV. Only the distorted power I'm drawing from the grid. So I hope now you can understand. So that is why in most of the time, my fundamental current quantity, is less than the distorted quantity, right? Or you can say distorted current. See, the RMS current, if you split fundamental current and the harmonic current, the rest of all the harmonics, the fundamental current is much less than the harmonic currents. That is why in some of the time it is reaching even beyond 100% of THD, right? This is one thing, right? I will also show you the power, so this is actually the power, this is actually the 33 kV side power drawn, right? What I want to show you is, I don't know how many of you can see this. Just see this, some of the time we are injecting the power back. See, this is the zero level. I hope you can see my cursor. See, this is zero level, right? I think this is a holiday, right? 30th and 31st is a holiday, Saturday, Sunday maybe. So those days during peak hours, that is 11 to 2 p.m., right? I'm injecting the power back to the grid. That's what you are seeing here, right? The quantity is somewhere around minus 300 kilowatt, right? I'm supplying to the grid, right? And also, if you see the current pattern, you can very well understand the what is it? The character of solar PV and its impacts. Sir, see, during night time, the load profile is somewhat flat during night time. See, this is actually the midnight, right? So during night time, the load pattern is somewhat flat. But see the daytime. See here, this how badly it is varying, right? So it means you are not maintaining any ramp up or ramp down from the grid. You are just like that. Whenever or as and when you need some amount of power, you are just drawing. The next moment, your power requirement is decreasing, or the next moment, just like the power requirement is increasing. So all these things are supplied from the the grid. So this is not acceptable in a small grid environment, right? Definitely, you should maintain some power ramp up or down, right? So that's what the things you should understand, right? This is one thing. The next is actually we have discussed, right? We are connected to the distribution system, and we have some mode of energy storage, and this is the the what is the charging points, right? We have considered only our the VIT campus with the people who are having four-wheelers, right? Just we have calculated during the daytime, our demand is going somewhere around 6 megawatt, right? During daytime, because it's like a swap. From hostel side, the load is very less, but from the academic side, the load is high, right? It's going around 6 megawatt, and of course, we are getting around 1.5 megawatt from the solar PV, right? In this case, right, it means you can consider some some kind of frequency issues or voltage issues are happening, right? So from the help of the energy storage and the smart charging station infrastructure, right? This we have realized in our PHIL environment, and we assumed our all we have modeled the buildings to a flexible load, or to a particular algorithm, particular pattern we have assumed. So it consists of AC load, how the AC load will varies, right? And lighting loads, lifts, right? Then water pumps, everything we have modeled, and we have realized in a power hardware load. So during daytime, when the solar varies, right? Uh, definitely you must be understanding, like the solar what is it? The generation is not like most of the time we used to think that the solar will start around 6 a.m. something like this, and will reach its peak and will come back, right? uh, if this is the case, it's fine, right? It is expected. It means it is the nature of solar PV. That's fine. But if it is having large variations, right, something like this, the power down, right, or the power ramp up or ramp down is is very difficult. It's very difficult to manage from the rest of the elements, or from the rest of the source. For example, uh, let us assume there's a power cut. We are running, or we are giving the backup from DG, right? No DG can handle this much of power ramp. Let us say this is around, see, let us talk very precisely. It is 800 kVA DG set, and my solar PV variation is somewhere around 400 to 500 kilowatt, right? Somewhere around 500 kilowatt. So none of your DG can take all of a sudden from 100 kVA or 200 kVA to the full size, because there is a shortage of 500 kilowatt from solar, because the generation was suddenly decreased due to some unknown reasons, right? So if they see that too, when we have a 2 megawatt size of solar PV, the variation can go from somewhere around 300 kilowatt to even 1500 kilowatt. I'll show you some examples from our SCADA based solar monitoring system, right? So that you will understand. I will show you the SCADA monitoring of our site, our solar plants. See, can you understand? This is the solar generation profile, right? See here, around 1050, for no reasons, right? From this, right, 628 kilowatt to it is falling down to 460. This is from 1 megawatt, right? I'll show you that. This data we are getting from one particular 1 megawatt plant in our rooftops, right? So for 1 megawatt, the change in power generation is from 628 kilowatt to 466, right? So see, this is somewhere around 200 kilowatt, right? So if you assume 2 megawatt plant, we have another SCADA system for one more megawatt. So if you consider that somewhere around 400 kilowatt, right? If there's a variation of 400 kilowatt within very short period, it is very difficult for the DG sets or any kind of things to manage, right? And of course, so you must be knowing that in February the generation will be very good. So this from 1000 megawatt or 1000 kilowatt solar plant. Yesterday we got around 4454 unit. It means 1 kilowatt is producing more than 4 units per day. This of course is a very good thing actually. But at the same time, see here, it's not too many variations, but simply within 3 days, right? During I think Sunday. So not Sunday, Saturday, we have just got only 2079 units, right? And the previous day we got 4503 units, right? So now at least you must have got some idea like how badly varying between a day, even within short time, right? So all these things should be managed properly by your infrastructure. That too, if you have a charging stations, right, with a rapid charging facility, then it is very difficult to manage everything, right? Because we are not sure like when the power generation will go down and when it will ramp up, right? So all those things should be taken care. That's what actually the topic or talk about the infrastructure, right? Okay, so I'm done. To clear, right? I'm open. Please, you can ask me. Ma'am, Vijay Lakshmi, ma'am.
Sir, sir, confirm here, sir.
Yeah, Karpo, ma'am. Ma'am,
Yes, sir, yes, sir.
முடிச்சிட்டேன். யாராவது கேட்கணும், ஏதாவது கிளாரிஃபிகேஷன் இருந்தா பார்க்கலாம் மேம்.
Okay, sir. Okay. Okay. So, dear participants, any queries, please post it in the chat box or unmute yourself and you can ask questions. Any queries?
Okay. No, if there is
Okay,
no things actually, see at present, my research group, right? We have a smart grid research group. with 4 faculty members and 12 PhD research scholars. Our team is mainly working on hybrid energy storage system and its role in smart grid environment or smart microgrid environment, and how it will support to the charging stations, smart charging stations. That is one thing. Second thing, how to enhance the life of energy storage system. See, I'm not talking about EV's battery. I'm talking about the charging station, or if you have a smart community, and in that, if you have energy storage, then how to enhance the life of the storage, like how to put the battery into 2 groups, and how the super capacitor, or the flywheel, or super energy storage system can help in high ramp up or ramp down of power requirement. So that's one another area. And also the power quality issues, as I shown in this, right? See, there are too many askings, or you can say the stringent what is it, regulations from the electricity board, that you are not supposed to draw beyond above 8% TDD, THD, right, or the total demand distortion. If that is the case, and if I'm equipped with good amount of solar PV or any other renewable sources, how I'm going to handle that, right? See, there's another group in my research team. We are working like when solar PV and VFDs of your lifts, or your we have a big chiller plant in our VIT. That's around 3 megawatt load actually. So we have 11 into 500 kilowatt chiller unit that is supplying because we have a centralized chiller station. So from that we are supplying almost all the buildings. So 11 into 500 is megawatt of load is fully with VFD, variable frequency drives. So I have solar PV, I have VFD load, very good amount, and also I have UPS. Most of the things are UPS with the active front end. So if all these things comes together, right, the interaction between, of course, we do have this also, right, active power filter. So the interaction between a constant, or you can say current source, that is solar PV, and we have VFD non-linear load, and we have active filters and all other non-linear loads. When you have these kind of things, how dynamically the grid impedance will vary. Because of the huge variation in grid impedance, what are the impacts, or what are the bad effects we are facing in the front end rectifier? See, when you have I'm just telling you an example. If you take active filter, solar PV, and VFD based load, and UPS, all these 3 are almost non-linear, right? When you have all these 4 in parallel with the grid, right, the effective impedance seen by the solar filters, or by the VFD active front end, or the active power filter will drastically change. Finally, what I'm trying to say is, when you have too many non-linear loads, or you can say current sources parallel, the effective impedance seen by a VFD, right, from the grid side will dynamically change, or you can say will drastically change. If that happens, the the impedance offered to the higher order frequency or higher order components will come down, because we are connecting too many sources in parallel. So the effective impedance offered to the higher order frequency will come down. So because of that, the higher order frequency component entry to the VFD, or entry to the UPS front end, or to the active power filter will increase considerably. That will for sure will affect the front end rectifier. It means the life of the front end rectifier will go. So this is also a research, one active research we are doing along with the Danfoss India Private Limited. So one of my student published a very good paper in this area also, how the grid impedance is dynamically changing because of the solar PV, because of the active power filter, or because of the VFD and the active front end of UPS. So because of all these things, how badly it is interacting with each other, and because of that, what is happening to the front end rectifier, right? So the life estimation we are doing, and we have got good publication in that also, and that is also one result. You see, this is also related to smart grid, because we are going to have, not only just one grid, there are other distributed generation along with this non-linear loads. So how badly it will play between each other, right? So that is also one area we are actively doing the research. And as I told you, power management, energy management. So this is also we are doing. Yes. So from this also you can ask something, or if you want any, research help, yes, we can do in the offline. Can you have any
Sir, there
training
is a
websites or links for studying the solar powered EV products or research solars? I can share Turam G. Yes, sir. I will give some, maybe I will give it to the organizer later. Then from all these papers are from a particular research group. So you can get the contact details from them, right? Of course, we are also doing, right, but some of the results are not yet published. So I cannot share just like that. But once it is shared, I will share the link. You can go through it. And what I'm trying to say is, like, many research groups are actively doing this. The green power based charging station, right? Uh, you know, the coordinated charging, as I told you, smart charging stations, everything is dealt by a groups. So you can just get this, and you can visit their website. You'll get a lot of data. And other things, questions are?
Sir, one more question in the
Yes, ma'am. Yes, ma'am.
chat box, sir.
The gout is coming up with many promotions for promoting vehicles. What do you think about the time it would take to reaching last 50% market? Sorry, reaching least 50% market, current infrastructure, as the Tesla is also emerging in the market. Uh, Ma'am, sorry, who's this?
Akash Manoharan.
Akash,
Question is
okay.
from Akash Manoharan.
Professor, what I can say is, like, the growth rate, right? Of course, it's very difficult to predict, but what we can say is, Indian grid, yes, even at present, we have huge variation. I can tell you one example, how we have handled this kind of, situations. See, 2019 September and October, right? Forget about Indian grid, especially Tamil Nadu grid. They have operated the grid with 65% plus from the wind power. You must be knowing that our average maximum or average demand can be somewhere around 10,500 megawatt. Out of this, more than 6,500 to somewhere around 7,000 megawatt of wind power. The most of the installed capacity is producing the power. So we have managed more than 70% of the required power from the renewables itself, right? If that is manageable, definitely even 50% of the what is that, the growth in EVs and its charging infrastructure can be managed. But the thing is, like the smart grid, codes, or you can say the grid codes. If you see the grid codes, the recent grid codes, we have relaxed the frequency, like 6 or 7 years before. It means like 2013, I think 2013, the grid code was somewhere refined, especially European, right? They refined, or they have changed the frequency limit, or the allowable frequency limit was somewhere around plus or minus 2%, right? And because of the huge penetration of the renewables, they have relaxed to somewhere around 5%. It means because of the large penetration of renewables, it is understood that the frequency will go up and down because of the highly intermittent nature of the renewables. And relaxing. So in the side, or along with that, the LVRT, HVRT, right? Low voltage right through capability of the renewables. Everything is getting adjusted. So it means the 50% growth of any make electric vehicles can be manageable, but only thing is at present we cannot go very high energy storage capacity at the grid level. That's very difficult. That is costly. But I'm sure. See, once if the Indian researchers are coming with a strong base from the NAS battery, sodium sulfur battery. Yes, we do like Indian from Indian grid also. We can give lot of test data to the rest of the country. I'm sure, right? Because lithium ion, it's like a monopoly market because of the availability. Lithium ion is very costly. But once if NAS, see, I can tell you, many of the Indian researchers who are working in materials on energy storage material, they have, the recent publication shows that they have very strong record, or they have very strong proof that once if NAS is allowed to a commercial level, definitely India also can do a lot of things in energy storage. That too, grid level energy storage system. I think only these two questions. Akash Manoharan sir.
Yes, sir.
Like, I don't know whether I have exactly answered your questions, but the thing is, the current infrastructure, yes, in the past we have managed with a huge renewable energy penetration. That is, I told you 70%, whereas other countries are thinking of 30% renewable energy penetration and its control. But we have managed more than 65%, 70% in the past. So it means with that kind of expertise, we can manage very easily with high penetration of EVs also. But only thing is, we need to do some kind of what is that retrofitting in the existing transmission or distribution infrastructure. Can you suggest a project?
Any queries?
Yes, ma'am. That's what I'm doing. Can you suggest a project for improving charging capacity of electric vehicle? Ma'am, I didn't understand. Like, what is the charging capacity? You mean to say the range, charge per that miles per charge, or what do you mean? Sasikala, madam. Ma'am, can you spell it properly? What does this mean? Charging capacity of electric vehicle. Hello? Sasila ma'am, can you hear me? Like, what do you mean exactly? Okay, no idea. Project for improving charging capacity. Maybe charging speed you're asking? Okay, that's fine. Yes, ma'am. Vijayalakshmi ma'am, it's fine.
Yes, sir. Yes, sir. Participants, any other queries, please? Okay, sir. We'll wind up the session. Thank you, sir. Thank you for your presentation.
Thank you, ma'am.
Thank you so much, sir. Token of appreciation brings out the excellent with us. So with this, in this delightful occasion, on behalf of management, on behalf of organizing team, I express my sincere gratitude to our today's resource person, Dr. K. Palanichami sir, Associate Professor, VIT Vellore, for sharing his wide research experience on EV, charging infrastructure, types of charging systems, impacts of charging infrastructure, smart grid and its stability, SCADA-based monitoring system, and upcoming area towards the development of a EV infrastructure. Thank you so much, sir, for making the session as a purposeful and interactive manner, and spending your valuable time with us in this grateful occasion. So thank you so much, sir. So I thank all the participants for your valuable presence and participations. Thank you all once again. Happy learning. So thank you so much. So afternoon session will start at 2 p.m. Thank you.
Hello, good afternoon, sir.
Yes, sir.
Please share the feedback link, sir.
Yeah. Already shared, sir. Please.
Sir, is a feedback link are considered as attendance, sir?
Yeah, yes. Both are same, sir.
Both are same.
Yeah, sir. Feedback link will be considered for attendance.
Okay. Thank you, sir.
Thank you, sir. Thank you. Sir, thank you so much, sir. Thank you.
Okay.